Hey guys, chapter 7. This is the last section we'll be going over in this chapter. So applications of the normal distribution. And here we have a standard score. So if you guys were worried about this last time, it's back to haunt you. So suppose that a random variable x is normally distributed with the mean, mu, standard deviation, sigma. Then the random variable z, the z-score is going to be that value of x minus the mean divided by the standard deviation. And that is normally distributed with the mean of 0 and a standard deviation of 1. So this would be the normal distribution. So standard normal distribution will always have those two characteristics. Standard normal distribution will always have the mean equal to 1. Mean equal to 0 and standard deviation equal to 1. If a normal random variable x has a mean different from 0 and a standard deviation different from 1, x can be transformed into a standard normal random variable z, whose mean is 0 and the standard deviation is 1. So that's what we find the z-score for, because we have a bunch of different distributions. So that could be a normal distribution. This could also be a normal distribution. This here could be, well, not that, but something that looks like this could also be a normal distribution. And we're comparing all of these to the standard normal distribution that we see here. And we're able to do that with finding the standard score or the z-score, and we could go from there. So this here is your standard normal distribution or your standard normal curve. Again, the mean is always going to be 0 and standard deviation is always going to be 1. So within 1 standard deviation, we have 68% of the data. Then 2 standard deviations, we have 95, and so on and so forth. But from here, what we're looking at, the standard normal curve is always going to measure the area to the left or from the left. So to the left of whatever the z-score is, that's our area. And the table 5 gives you the area under the standard normal curve. But what we're going to use is Excel, because you get more of a range with that. So the standard or the table in the back of the book is always going to give you these different variables, but they're not going to be exact. They're not going to give you a bunch of different decimals after your decimal place. They're not going to look at, they're only going to look at 3 decimal places of your standard deviation or your standard score. So it's only going to be 0.123. It's only going to give you those values there. So we use Excel. And let's look at this. So IQ scores can be modeled by a normal distribution with a mean of 100 and a standard deviation of 15. An individual whose score is 120 is 1.3. And the way they did that is they just plugged it in. So they said X, what was it? X is 120. Then we had our standard deviation, or I'm sorry, our mean here was 100, and they gave us the mean right here. And lastly, the standard deviation was 15, and they gave us our standard deviation here. So that's how they came up with this. They just subtracted the 2 at the top and then divided by 15, giving us 1.33. Again, we could be a little bit more accurate if you wanted to. We could head over to Excel, but for right now, this is how they ended up finding these values. And the way that we could find these values on Excel, let's just write this information down. X equaling 100, the mean equaling 100, X equaling 120, and the standard deviation being 15. And taking this over to Excel, we have X 120, the mean is 100, and standard deviation is 15. And the way we could find our z-score Z equal to X minus the mean divided by the standard deviation. Z in this case is going to be equal to, our numerator is X minus the mean. So X minus the mean, and we're dividing that by the standard deviation. And there we go. That's how they got that 1.33 that they have right there. 1.33, we got a little bit more than they did, and that's just because we're using Excel. And now the next thing that they did is they found that on the standard normal curve. So the way we could find that on Excel, remember this is a normal distribution. So we could say the probability of X being less than 120, because remember, our curve is always going to measure from the negative infinity up to that point. So everything to the left of whatever our value is. So here we would hit equals, this is a normal distribution. So we have these two different ones, normal distribution and normal inverse. Normal distribution is going to give us our standard deviation. I'm sorry, normal distribution is going to give us the area. Normal inverse is going to give us our z-score. So here we want the area. So we're going to click on this one here. And here you didn't even have to do all of this. So we could plug everything in. So X in this case is 120. Next, they're asking for the mean. The mean's 100. Standard deviation 15. Cumulative. And for all of these, for all of the normal distribution, we're always going to put true because we want the entire area under the curve, not just the area around that value. And there we go. So 0.908. 0.9082. That's exactly what we had over here. Oh, actually, we got something a little bit more accurate. So we got a little bit more because we didn't just use 1.33. We used 1.33333. Going back to what they said as well, we could have used the standard normal curve. So using the standard normal curve with the mean of 0, standard deviation of 1, we could have still used normal distribution, but this time X would have been 1.33. The mean would be 0, standard deviation would be 1, cumulative true. And we got the exact same thing. So here you could have used either or. This one here is standard normal. And what this means is that the mean is equal to 0, standard deviation is equal to 1. So this is a standard normal distribution. But using this one, we use the data for that specific problem. So that's the difference between the two. We either use a standard normal curve or just a normal curve with our information input into the system for us. Either way, we ended up with the same results because all of this does is it does the work for us. It finds a z-score, and from the z-score, it gives us our area. Exact same thing that they did over here. And use a complement rule to find the area to the right of 1.33. So what we did here, this here is looking at the area. We found our z-score of 1.33, or we'll just say 1.333, and that found the area to the left of that. And notice how we put the exact same thing here. So the area to the left of 120, or we could actually put that. And now to find the area to the right of 120, we could use this blue shaded region. And now the probability of X being greater than 120 It would just be the complement. So we do not have a way on Excel to start here and stop at positive infinity. So what we do, because the area under the curve is always equal to 1, we could just find the complement here. So equals to 1 minus our other value here. And this is how we get this, 0.0912. And coming over here, the area to the right of that value is going to be the complement. So that's how we would have them. All right, so now looking at this, we have one of our first examples. So a pediatrician obtains the height of her 3-year-old female patients. The heights are approximately normally distributed with a mean of 38.72 and a standard deviation of 3.17 inches. Use a normal model to determine the proportion of 3-year-old females that have a height less than 35. And let's take all this information down. So first things first, heights are approximately normally distributed. Perfect. So because they're normally distributed, we could use a standard normal distribution to identify whatever those values are. Next, with the mean of 38.72. So the mean is equal to 38.72. And a standard deviation of 3.17. Standard deviation 3.17. Use a normal model to determine the proportion of 3-year-old females that have heights less than 35. So X is less than 35. So what we're looking at here, just roughly looking at this, 35 is less than 38. So where we have 38.72, remember the mean is always going to represent the highest part of our normal distribution. 35 is less, so I'm just going to draw this line over here. And we're looking for the area less than that. So now plugging this into Excel, let's get a new page. So mean of 38.72. Standard deviation of 3.17, and we're looking at X being less than 35. So here, the area, the probability, or the proportion, remember there's two different definitions there, so it could either be the probability or the proportion, but the probability of X being less than 35 is equal to, we're using normal distribution. Normal distribution, X in this case is 35, with the mean 38.72, standard deviation 3.17, and cumulative true because we want the entire area under that curve. And there we go. So we would plug this in, and the area here is 0.12029, so 1203. And we come over here. These are the steps that they took, and they converted it into a z-score. We didn't have to convert it into a z-score because Excel does that for us. Yeah, so we didn't have to do all of that work because Excel did that work for us. My apologies, let's clear this out. So from there, they looked at standard deviation, or I'm sorry, that z-score up in the standard normal table, and they got roughly what we got, but remember they're cutting it off at 1 point or a negative 1.17. We're cutting it off at something a lot greater than that. Well, not greater, a lot more accurate than that. So our decimal approximation here is going to be just a bit different than what they get over here. Lastly, the normal model indicates that the proportion of the pediatrician's 3-year-old females who are less than 35 inches tall is 0.1210, or in our case, 0.1213. 1203, something like that. All right, now using technology, how did they find it? So figure shows from Minitab, so they use Minitab in this equation. See how they got something a little bit closer to what we got on Excel. Next, because the area under the normal curve represents a proportion, we can also use the area to find percentiles or ranks of scores and so on. So with that, so recall that the kth percentile divides the lower k% of the data from the upper k% of the data. So remember, I believe this was back in chapter 3, we had our line and where quartiles break up the data into 4 pieces. Percentiles break it up into 100 different pieces. So I know this isn't 100, but let's just pretend that it is 100. Looking at this one, the percentile, we'll say that's 50. The 50th percentile represents 50%. So with this one, we're looking at all the area to the left of that. And for data where we're representing the tops or the bottom 75%, or that looks more like 80. So 80 is going to represent, we're going to look at the area to the left of that, which would represent this area here. So now looking at this, for the pediatrician presented in the previous example, find the probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall. So with this one, because we're looking at the middle area, so looking at this here, let's see what the mean was. So the mean was 38. And we're looking at 35 to 40%. So here at 35 up to not 40%, but 35, a height of 35, height of 40. So from here, we're looking at the area between these two values. And in order to get that, what we first have to find is 40%. Not 40%, I keep saying percent, I'm sorry. So this was 38 point something, 38.72. Or we could just keep it over here, 38.72. First, we're gonna find 40, and that's gonna represent all of this area over here, all the area to the left of 40. But since we grabbed data that we shouldn't have, we grabbed too much data. Over here, if this represents 35, what we would have to do is find out what this area is, so that way we could subtract it to just get that 35 to 40. So again, first thing we're going to find is the probability of X being greater than or less than 40. So probability of 35 less than X less than 40. This is going to be equal to the probability of 40 of the X being less than 40, and we're subtracting probability of X being less than 35. And those are the values that we're going to have. So here we have the probability of 35. So again, probability of 35 less than X less than 40. This is going to be equal to the probability of X less than 40 minus the probability of X less than 35. And it's not going to let me do all that. All right, so there we go. So now we're going to look at the probability of X being less than 40. Then the probability of X being less than 35. So X less than 40 is equal to, again, this is a normal distribution. Normal distribution, we're looking for the area. X, in this case, we're starting off with 40. So 40 with the mean of 38.7, standard deviation 3.7, 3.17. cumulative are always going to be true for a normal distribution. And that's this area up to 40. So it's all of this black shaded region. Now we have to find this yellow shaded region to see how much we take off. So equal to a normal distribution. This time X is 35 with a mean of 38.7, a standard deviation of 3.17. Cumulative true, always true for a normal distribution. And lastly, to finish this off, the probability of 35 less than X less than 40. This is equal to this black shaded region up to 40 minus the amount that we overshot, that 35. And there we go, 0.5365. So this is the probability, let's see, how do we state it? This is a probability that a randomly selected 3-year-old girl is between 35 and 40 inches tall inclusively. So these two are actually exactly the same, less than or equal to or less than, because we can't really identify where the less than or equal to part is on a normal distribution. So here that's what those are. And let's see if we missed anything. So again, what we're looking for is this entire area up to 40, and we're subtracting how much we took or how much we overshot. So that's how they found the 35th percentile or the 35th z-score, the 40th z-score. So we have those two values, and they went over to the table and found the two values. And on technology, how did they do this? So they used the TI-84 plus calculator. We used Excel, but no big deal. So now the interpretation, if we randomly selected 100 3-year-old females, we would expect about 53 or 54 of them to be between 35 and 40 inches tall. And they got this 53 or 54, 53 or 54 based on this value right here. So 53%, 53.65%. So it could be either one. And now looking at this approach here, so this table is going to kind of help us with identifying what our area should be. So area to the left of the X value. So we have our X value, everything to the left. We don't have to do anything crazy because it already gives us this area here. Whenever we're looking at data to the right of our values, we're using the complement because Excel is always going to give us the area to the left of those values. So 1 minus whatever the area is right here, this white shaded region, to get this blue shaded region. And now for in-betweens, whenever we have data that looks like this, the in-between area is going to be a little bit different. So we're always going to find the value of the rightmost value. And from there, we looked at that entire area from negative infinity up to that point. And to find this shaded region, we just have to find the area to the left of our smaller value to see how much we have to take off. Because again, whenever we do these, we're finding the entire area here, and we need to know how much to take off on this side. So we find those two different areas and subtract them. Some cautionary thoughts. So the normal curve extends indefinitely on both directions. So for some reason, there is no range of values if a normal random variable for which the area under the normal curve is 1. So even though I'm drawing graphs like this, we know that these extend to infinity on both ends. And that's all they're saying here. Even though these values are unrealistic, so they were talking about heights of 3-year-old babies. So this was 38.72. Yes. So 7.2. Even though on the graph, these extend on forever, this value could possibly be 200 inches tall. So 200 inches tall is really, really tall. Let's see how big of an exaggeration that was. So 200 inches, we're dividing that by 12. dividing it by 12 inches to see how many feet. That's 16 feet tall. So even though this value here is unrealistic for this problem, we still have to account for this area over here. Again, it's very, it's not even unusual, it's uncertain. Like the probability is going to be 0, but for the sake of the problem, for the sake of the normal distribution, there's still some sort of probability where it would be, where we would have those values. All right, so that's what they were talking about there. So for example, if we asked to find the area under the standard normal curve to the left of 40, with the mean 15, standard deviation of 2, StatCrunch, as well as other software and calculators will state that the area here is 1. And that's just because they're not being super accurate. So remember on Excel, those values are going to be a little bit different. You're going to actually get scientific notation, x equaling 40, mean equaling 15, standard deviation equaling 2. And we're looking at the area to the left. So x is less than 40. Let's see what it gives us. So again, for this data right here, we're saying x is 40, mean is 15. And standard deviation, I'm just going to leave it like this for right now. Standard deviation is 2. The probability of x being less than 40, that's equal to normal distribution with a x of 40, mean of 15, standard deviation 2, cumulative true. And this is equal to 1, but because we don't have those values, like, or we could see, let's try 1 minus all of this. Oh, they don't even have it for that. So I don't have scientific for either one of those. All right, so because of that, here they, well, that proved me wrong. No big deal, but here they're saying that even though that area does exist over here, it's still going to count it as a probability of 1, just because it's going to be majority of the data, nearly 100% of the data, so nearly 100%. And we will follow the practice of reporting set areas such as 0.9999 or greater than 0.9999 as 1. And similarly, if software reports an area of 0, we will report the area as 0.0001. So looking at those two different ones, they're just, this is kind of just like a disclaimer for whenever you're doing the homework. If your area is equal to 1, we are just going to say greater than 0.9999. If your area says 0, we're going to report the area as less than 0.0001. And objective 2, so find the value of a normal random variable. So looking at this, the height of a pediatrician's 3-year-old female patients are approximately normally distributed with mean equal to 38.72 and standard deviation equal to 3.17. Find the height of a 3-year-old female at the 20th percentile. So 20th percentile, or the way that's denoted is P sub 20. 20th percentile. All right, we're coming over here. Let's get another page. All right, here at the 20th percentile, let's draw that just to see what we're looking at. So remember, percentiles are always going to be measured from 0 up to that percent. So if we have 20% right here, we're looking at this area right here. And 20th percentile, the percentile portion is representing an area. So this here is 20%, or if we were to put it in a decimal form, it would be 0.20. So let's write that down. The mean is 38.72. The standard deviation is 3.17. 3.17. And the area is 0.20, or just 0.2. So now this time we're looking at an area and we need an associated z-score. So whenever, like our question between inverse and, let me just show you. So P sub 20. So equals normal distribution. So we have these two here. We either have distribution or we have inverse. Distribution we use for area. So when we need area. Inverse is when we have area. So now for this, we're given this, they're asking us for the 20th percentile. We drew our beautiful picture and we have an area. So this black shaded region is our area. And what we're looking for is an associated z-score. So this time we have the area that we need the z-score for, and we could just go from there. So area here, they're asking for probability. So probability does represent the area. So probability 0.2, mean 38.72, standard deviation 3.71. And here they're not going to ask whether we need cumulative or not, because it is a cumulative, right? It is a accumulated area from 0 up to that point. And there we go. So this here is our value. So how can we say it? So the interpretation is the score. Was it score? No, it was the weight. Weight of 3-year-old females in the 20th percentile are less than, because we're looking at the area to the left, less than 36. What did I do? 36.052 inches. And there we go. Again, one thing that I want you to take away from this part of the lesson is whenever we're looking for our distribution, so equals normal distribution, normal inverse. This S is just for standard, but we don't have to use these. So normal distribution or normal inverse. A distribution is when you need the area. Inverse is when you have area. So here we had area, we used inverse, and that's how we came up with all of these different values here. Let's clear this out. And let's see what they tell us. So again, we're looking at the area that represents the left 20%, breaks up the left 20% from the right 20%. Here they found this value of negative 8.04. And it's really close, it's not exact. So that's why their value came out. Oh, they use a z-score. And from here, they're turning that z-score into a standard or the actual value here. Just so you guys see this part, when we have this, the z-score was equal to x minus the mean divided by the standard deviation. So all they did here is they looked and solved for x. They multiply both sides by sigma. So these two were divided out. And I'm just going to switch the sides. X minus the mean is equal to standard deviation times the z-score. And from here, they added the mean to both sides. So from here, they just said that x is equal to the mean plus the standard or the z-score times or standard deviation. And that's how they found out what x was. So you guys could do all of that, but Excel does all of that work for us, and we're able to just type that value in there. So they do a little bit more work. You could definitely learn from this part too, but again, Excel does that for us. All right, so the 20th percentile separates the bottom 20% from the top 80%. And that's how we're able to see those. And these values too, in StatCrunch, they gave them those values there already. But they didn't state the interpretation. No big deal. All right, so looking at this quote, scores earned in the mathematics proportion of the SAT, a college entrance exam, are approximately normally distributed with mean 516 and standard deviation 116. What scores separate the middle 90% from the test takers from the bottom and top 5%? In other words, find the 5th percentile and the 95th percentile. So going off of what they're asking, they were looking at the middle 90%. So here in the middle, we would have 90% of the scores from the bottom 20 or 5% and the top 5%. So they told us that 5% would be here and 5% would be here. Another fun thing here, if we add all of these percentiles, we get 100% of the data. So 5 plus 90, 95 plus 5 gives us 100. So that's 100% of the data. All right, so the first thing that we would want to do, because we're looking at just this middle area here. Oh, this looks terrible. I'm sorry. But we're looking for that middle portion there. So what we're going to do is first find the left area. Just roughly highlight that. So the area to the right, or the right value, then look for the left value because we clearly overshot it. So let's first look for this yellow area. So that would be the 90th percentile. And coming over here, let's clear that up. So coming over here, in order to get the middle 90%, we're looking at the 90th percentile, or actually that would be the 95th percentile, because looking at these two areas together, 5% plus 90% would give us 95. So looking at the 95th percentile, that's going to be equal to normal. Is it normal distribution or normal inverse? Do we need an area or do we have an area? Here we have the area of 5% and 90, so we're going to use normal inverse because we have the area. Here we're looking at the 95th percentile, so 0.95. That's a probability. The mean here, standard deviation here, and that's all we need for the 95th percentile. So this is a score that corresponds to that 95th percentile. And we don't have to do any subtracting or anything because we're just getting this value right here. So the value that we got, I'll do that here in red. So here that was 43.93, or we could just say 44. Oh, that's why it looks weird. We're looking at the wrong data. So let's get a new sheet and doing this over here. So we kind of looked at the wrong data. All right, so data for this problem, we're looking at the mean. So mean is 516. Our standard deviation is 116. And there we go. So we're first looking at the 95th percentile. So 95th percentile. All right, now looking at these values. So this was a 43 point whatever. So looking at the 95th percentile, we have the data that represents the top or separates the bottom 95% from the top 5%. So that's equal to a normal distribution. Is a normal distribution a normal inverse? Do we need an area or do we have an area? Here we have this area of 95%, so we're going to be using inverse, probability of 0.95. Mean here is 516, standard deviation 116. And there we go, much better. So this is a score that represents the 95th percentile, so 706.803. And that should be a 0, looks like a 6. 803. So we have that. Next, we're going to look at this percentile. So the 5th percentile, let's shade that region. 5th percentile, P sub 0.5. And here, normal distribution. So is it normal distribution or normal inverse? Do we need an area? Do we have an area? We have the area of 5%, so we're going to use inverse. Probability is 0.05. Remember that represents our 5%. I got the 0. There we go. Then the mean was given, comma, standard deviation, this. And there we go. So the bottom 5% would have gotten a 32 or 325.1969, so 197. So those are the two scores. So now for our interpretation of this problem, the individuals that make up the middle 90% of the data scored between 325.197 and 706.803. Or you could even think of it as like the whole numbers, because I believe these would be whole numbers. So scored between 325 and 707. And there we go. That's how the data would be displayed there. And let's see if they got something a little bit different. They might have, just because it's not exact. Whenever you look at the table, it's not going to give you the area of exactly 0.05, or maybe it will. At times it will, most of the time it won't. Just like here, they got the area of 0.0505 and also 0.0495. So they just kind of averaged those two variables out. And with that z-score, they got the scores of 325, which is what we got as our lower value, and 707, which is what we got for our upper value. So either way, you still get roughly the same thing. So technology, they use something a little bit different. What did they use? It doesn't look like they tell us. It might be StatCrunch or something different. And lastly, the interpretation. So SAT math scores that separate the middle 90% from the top 5% or the bottom 5% is 325 and 702. So put another way, the students who scored 325 on the SAT math is in the fifth percentile. The student who scores 707 on the SAT math exam is at the 95th percentile. So we might use these results to identify those scores as unusual, but we could still see that they are somewhat usual. All right, next, the nation, I'm sorry, not nation, the notation Z sub alpha, pronounced Z sub alpha, is the score such that the area under the standard normal curve to the right of Z sub alpha is alpha. So Z sub alpha, area to the right, is going to be alpha. It could also be area to the left at times too, or this might be known as C. So depending on what the problem, how the problem is stated, but alpha is always going to be the area. So find the value of Z sub 0.10. All right, so we're just looking at Z sub 0.10. So over here, let's get a new sheet. So here, what this means is that we have our data here. Z sub alpha is representing this right tail. And we have this here. So that tells us Z sub, if this value here is Z sub 0.10, then that tells us that this area here is 0.10. Remember, whenever we plug this into Excel, it's always going to read the data to the left. So if we just type in 0.10, it's going to think that we're typing in this value, going to give us a negative Z-score. And that's not what we want. So what we want is that Z-score. So the area associated with that Z-score is going to be, kind of drawing it just takes a while. All right, so it's this area right here. And what we would type in is equal to normal distribution. So normal distribution or normal inverse. Do we need an area or do we have an area? We have this area over here, and the area complementing 0.10 would be 0.90. 0.90. There we go. And there we would have 100%. So here we have an area, so we're going to use normal inverse. So normal inverse, there we go, area 0.90 with the mean, because this is a standard normal distribution, the mean is going to be 0, standard deviation is going to be 1. And there we go. So now the associated Z-score here is going to be, and that's a Z, that's going to be equal to 1.28155, so 1.6. Much better. And let's see what they got. So by hand, they found all of this. So an area of 1.28, we got 1.281. All right, I'll give it to them. And they typed it into their calculator, and this is what they got. Cool, again. And that's our slideshow. So if you guys have any questions, please email me as soon as possible. This should be the last section that you guys cover before exam number 3, so be sure to complete that. If you don't have any questions, good luck on your homework. Bye.